Okay, it's the 6th of September. We are talking about conversions, the units that you're responsible for, and we've run through one just simple straight-up conversion using powers of 10 and using scientific notation. Now let's talk about derived units. So, what is a derived unit? Oh, wait. Meters per second. Grams per milliliter. Kilometers per hour. Those are derived units. Okay? Ooh, I know. Meters squared. A derived unit, so derived units are anything we get when we multiply or divide multiple SI units. Okay? So meters squared, centimeters cubed, those are also derived units because we are multiplying SI units. Why are these conversions harder? Well, hey Hannah, they're a little bit harder because you've got something on the top and the bottom of that factor label line. Okay, so this is one that we very commonly run across in physics because we're very often dealing with the velocity of objects. And in SI, velocity is typically given as either kilometers per hour or meters per second. So we have to do the conversion so that our units match if we're doing a problem where we're going to need meters later on. When we get into force problems, everything's got to be in meters. We can't use kilometers, so anytime we're given a velocity in kilometers per hour, we got to get it to meters per second. You really want to be able to do this in one step or in one factor label at any rate, and you want to get proficient and fast at these because they're only a small part of a larger problem. When you do a conversion like this, you're really doing two conversions. You're converting kilometers to meters. You're also converting hours to seconds. And to do that, we still use a factor label, but we want to be really careful that we start off like that. That is the entire key to doing this easily. And I have a habit of writing my derived units like that with that sort of backslash thing, kilometers per hour, I know what that means. But I really force myself when I'm doing math with derived units to make sure that I am careful to do that. Because that reminds me that that's actually a fraction. We're actually talking about a numerator and a denominator. And that's critical because that allows me to do the factor label all in one step, which makes life so much easier. Now, that said, it doesn't matter what you start with. My habit is to start with the numerator. So if I'm going to convert that numerator, I'm going to put units here to match. And I want to be in meters. So one step, that's easy. And I'm going to dummy proof myself by putting my 1 in front of kilometers, kilometers immediately. And I know that that's 10 to the third meters. So at this point, if I check my units, kilometers cancel, I end up in meters. That's where I want to be for my distance component of the derived unit. Good. Now I have to convert hours. So you can do this as a 1 or a 2 step. I'm going to tell you that you will get really good at knowing how many seconds. Does anybody right off the top of their bat immediately know how many seconds are in an hour without thinking? Excellent! Okay, because it's 60 times 60. So it's 60 squared, which is 3,600. If you feel the need to still do this, you can. Whoops. Whoops. Jeez Louise, Moser. But it's much more elegant, and you'll get really good at doing it like this. Let me get rid of this, that, and that, and saying 3,600 seconds. Okay, so again, you can do it either way, but it's it saves you one step of calculation. If you just put that straight in as 3,600 seconds. You do this as an easy, power of 10 conversion. You can. It's not as clean and easy as the other ones. You're going to need a calculator. But if we convert these all, 1.15 times 10 to the second, convert this, 3.6 times 10 to the third, and I'm actually going to get rid of this one. I mostly did that so you know it's okay if you need to, but I'm going to encourage you to get accustomed to doing it this way. So now our setup is just 1.15 divided by 3.6, the whole thing times 10 to the 2 plus 3 minus 3. Hey, that's pretty slick. Our powers of 10 are going to be easy. So we've got 0.319444444 repeating times 10 to the second. We have to fix the scientific notation on this, obviously. And I have to draw dots under and over. There, I said it. I feel like a grubby little 5-year-old, but I can't reliably do the dots, move the decimal without doing bumps under. So 1, 2, 1. Okay, so I can either call this 3.2. Oh no, I have 3 sig figs, don't I? 3 sig figs. 3.19 times 10 to the first, or I could just call it 31.9 meters per second. Okay. Either one of those answers is acceptable. You don't have to put it in scientific notation unless doing so makes it easier. Typically, any number that's over 1,000 or under 1,000th, you probably want to put in scientific notation because it's easier to handle. With a number that's under 100, you can, if it's easier for you, and if you want to leave it not in scientific notation, you can do that as well. Okay. Is this something that you already felt comfortable with, or was there anything there that you were not familiar with in terms of doing derived unit conversions?
I remember doing like kilometers.
You wouldn't have done, you would probably never have done kilometers or meters. In chemistry, it's all moles, grams. It's really all mass and temperature measurements. Here we do both mass and velocity measurements, and we do a lot of derived units. So what I'm going to have you do is pull up the practice sheet on the plan. Okay, so what about when we have a derived unit for area or volume? So let's do one with volume. What the heck? Let's go crazy. So if I've got something that is 41.7 cubic meters. So if I were to put this in a square configuration, it would be a square that was 47.1 meters on each side. This is a massive volume of something. I don't know what. But just because I'm crazy like that, I want to know how many cubic millimeters that would be. These are really tough, and I keep saying I try to dummy proof everything because I make the stupidest mistakes possible. So I've found some tricks to not make them. You do the exact same thing to start out. By the way, is this color combination okay? Is the white on black better? Is this okay? Can you see this?
Yeah.
Okay. It is yellow.
Oh.
It is yellow. I didn't know if I needed to switch back to white. Sorry to mess with your head so early in the morning. So I know that I want to start there. I'm going to shrink this because I'm going to need a lot of space. Well, I know that there's a relationship between cubic meters and cubic millimeters. Now, I know the following. 1 millimeter is equal to 10 to the negative third meters, which means that 1 millimeter times 1 millimeter times 1 millimeter is equal to 10 to the third meters times 10 to the third meter, negative third, times 10 to the negative third meter. Ah, I just... Negative third, sorry. I got all excited and I went straight to the cubed. So I will tend, especially when I'm refreshing my memory, when I'm kind of ramping up to speed, I will tend when I do these problems to go ahead and put my 1 there and then put 10 to the negative third times 10 to the negative third times 10 to the negative third. That helps me remember that I'm cubing this value. So once you get past that, it's really pretty easy. It's remembering to do that, and obviously for squares it would be put in there twice. So I'm going to convert this to scientific notation, 4.17 times 10 to the 1 meters cubed. So now I have 4.17 times 10 to the 1, and this would be minus, I'm going to go ahead and do the math here. This is 10 to the negative 9th meters cubed. So minus negative 9. So this ends up being 4.17 times 10 to the 10th. This is a massive volume of something. I don't know what. It's big. Okay, does that help?